Hello, and welcome to the C++20 preview section. In this section, we will be learning about upcoming features that will be available in C++20, which will be released around February of 2020. Please keep in mind that everything covered in this section is experimental and considered both advanced and optional. In this video, we will be taking a look at concepts. Let's get started. Say you had to make a generic template function, but it would only work if both of the parameters passed in could be added together. So an int and an int are fine, or an int and a double, but an int and a standard string would crash your program. Using concepts, you can define constraint on the values passed in as the template arguments. And the best part is, they are evaluated at compile time, so you don't incur any runtime penalties no matter how detailed the constraint is. At their core, concepts are a compile time predicate, which means at compile time, they must resolve to true or false. Concepts can be made by building up on other concepts as well. Here, for example, we define a concept called integral, which constrains the type to pass the standard isIntegral test. Next, we create a signed integral concept. This says that the value must be both a regular integral and must also pass the standard isSigned test as well. And finally, we define an unsigned integral concept that says it must pass the integral constraint but fail the signed integral constraint. Concepts can also be more complex than just a single predicate. They can be a constexpr function that can be resolved at compile time. Here, for example, we have an incrementable constraint, which checks that the data type can be incremented using the ++ operator. We also have a hashable constraint that verifies that the value passed in can be run through a hash function and that its result will be a standard size t. As you can see, this makes concepts very powerful. To use a concept, you simply use the name in the place of the type name or class parameter in your template definition. As you can see here, the print unsigned numbers function has a template argument that must pass in a unsigned integral constraint. Let's check out some code, but before we do, we need to go over some caveats. First, to compile this example, I'll be using G++ version 9 with the -f concepts flag to enable concept support. If you don't have access to this version or another compiler with experimental support for concepts, you can use the compiler explorer at godbolt.org. Once again, these are experimental, unreleased features, so they are subject to change or just be broken. With that out of the way, let's go ahead and jump in. Okay, so I've got my project open. I'm on my concepts.cpp file. And the first thing I'm going to do is I'm going to concept. The first concept I'm going to create is the incrementable concept, which we discussed during the slides. Basically, this is going to check that if I pass in a data type t, that t can have the ++ operator called on it. This will not actually do the incrementation. It just says, will this pass the compiler? Will the compiler actually be able to compile this code? And if so, then it's good. Then it meets the concept constraint. But if the compiler cannot compile that code, that means it does not meet the concept constraint. I'm going to add a few more concepts as well. Here's the 3 concepts we also discussed during the slides: the integral, signed integral, and unsigned integral. Once again, the best way to think about concepts is, if I pass in some value, will the compiler be able to compile that code? Not will it execute, although it should execute, but the compiler has to be able to compile it. So some stuff you cannot do with constraints is actually check runtime values. That's not the purpose of constraints. Here I'm going to go ahead and create the print unsigned numbers function that takes in an unsigned integral parameter. If I pass in something that is not an unsigned integral, it will fail. We'll see an example of that. Next, I'm going to create another function called increment, and it will take in an incrementable type. So here I've created my main function. Here you can see that I'm printing an unsigned number. I'm printing the unsigned number 10, and I'm casting it to an unsigned type. Then I'm going to increment 90, increment 0.6, and increment 15L. And for good measure, I'll also increment hello. I'm going to save this. Now, to build this project, I've created a makefile, so I'm going to show you the makefile real quick. Basically, the makefile is just a script that will build our project. So we can see the CXX flag. I'm using G++ version 9, so G++-9 is the command. The C++ flags or CXX flags I'm passing are the concepts flag, so I can enable the concept support, which is experimental at this time. If I don't pass this flag, the compiler by default will not have support for this. And I'm also passing in the C++ 2a standard. Now, in most of our videos so far, we've been using the C++ 17 standard, which is the most stable, the last stable release. When C++ 20 is released, this flag will be updated to C++ 20 or 20. But right now, because it's still an experimental stage, it is the C++ 2a flag. Next, I specify the objects that I'm going to create, which is just a concepts.o, and then the binary I want to build, which is the concepts binary. The rest of this you don't really have to understand, but if you want to, basically these are just the instructions on how to actually build the program. The last directive here, the clean, is just a simple remove of the objects and remove of the bin so that it will clean the workspace. So now I just type make, and there we go. My program has been built. And if I run it, it shouldn't look like anything too special. The first one was where we printed the unsigned 10. Then I incremented 91, I incremented 0.6, I incremented 15, and I incremented the string hello, because the string operator actually has an increment operator overload built into it. So let's see what concepts actually provide us. So that worked well, but let's see here. What happens if I delete this? If I just pass in an integer 10. Now an integer is not an unsigned type, it's a signed type. So what do we think will happen? Here we go. It says that error, we cannot call the function print unsigned numbers with t equals int because the constraint is not satisfied. The unsigned integral constraint cannot be satisfied with the int type it evaluated to false, specifically the signed integral int evaluated to false. So this is actually really cool because this gives us a much cleaner output of what went wrong. It wasn't at runtime. It was at compile time, so I can actually fix this. And to fix it, like I showed you in my original example, all I have to do is just cast this to an unsigned type. Like that. No big deal. So what about my incrementable? Let's go ahead and actually create our own structure that will be incrementable, and then we can play with it. So I've created this struct here called blah because it's just a throwaway, and it has the increment operators defined, and I also defined the output override so that we can actually output it to cout. Next, I'm going to get rid of that string 1, and I'm going to create a blah, and I'm going to increment blah, and if I run it, we can see that blah struct is output, which is what my operator overload did, which you can see here. So blah struct is output. So this worked beautifully. Now what happens if I just go ahead and delete all of that? So now we get an error at compile time. It says that we cannot call the function void increment with a type of blah because the increment constraint is not satisfied. Basically, the blah cannot have a plus plus operator executed on it. And that's a problem because our function requires that a plus plus operator be executed on it. So that is the power of constraints. And you'll notice if you've ever had the template errors that these are much, much nicer than the template errors that you see. This is very clean and very easy to figure out what went wrong. Once again, if we put that back and we make again, it builds and runs just fine.